On to question 3. We've got a crane that's lifting a container 30 meters in 15 seconds. The weight of the container is 60,000 newtons. Calculate the work done by the crane in lifting the container 30 meters. So the work done is energy. You've effectively got two equations that you might use here. Work done equals force times distance, and potential energy or gravitational potential energy equals mass times gravitational field strength times height. The fact that the weight is already done for us means that we don't need to work out mg. That's already given us force, and so either of those equations are effectively the same thing. So the weight force 60,000 newtons, the distance 30 meters, and the unknown work done. Substitute that into our equation for work done, gives us 1,800,000 joules. Remembering that work done and energy are the same thing. In part 2 we have to calculate the power of the crane, and so the equation that you've got for power, the front of the booklet, is energy or work done divided by time. So we use the work done from part 1 and we divide that by the time of 15 seconds. So that gives us 1,800,000 divided by 15 comes out at 120,000 watts or joules per second. So when the container is just hanging in the air without moving, what work is being done? If a force is being applied but it's not being applied over any distance, then according to the formula work done, there's no work done equals force times distance. There's no work being done because the distance is not changing. And so using that formula, if d equals 0, then the value for work done must also be 0. Okay, and in part C we've got the force diagram below. Explain the link between the vertical net force acting on the container and the type of motion produced while the container is being lowered. So we've got to describe what is meant by net force and explain the link between the direction of the vertical net force and motion. So the first bullet point, and I'd always recommend that you tick off each bullet point as you do it, just to make sure you're keeping track of what's been done and you're checking that you haven't missed anything at the end. The net force is the remaining force when opposing forces have been accounted for. So we might use words like resultant force or the overall. So if the large arrow represented 20 newtons and the smaller arrow represented 8 newtons, then our net force would be 12 newtons, 20 minus 8. So in this case the larger downwards force is opposed by a smaller upwards force, and that means that the net force is downwards. And bringing that unbalanced force into linking it with motion, an unbalanced force produces acceleration in the direction of the unbalanced force. That's Newton's second law of motion. And so that acceleration will be downwards as the container is being lowered. So the container will accelerate downwards as it's being lowered. Alright, final question. The crane was lifting another container and the cable broke. It was a 6,500 kilogram container and it fell 15 meters to the ground. The container had 970,000 joules of kinetic energy just before it hit the ground. We've got to calculate the energy the container had before the cable broke, and then explain why there is a difference in the energy from when it was hanging to immediately before it hit the ground. So we're going to be using the gravitational potential energy formula, EP equals mgh, to work out the energy before the cable broke. We're going to compare that to the value that we've been given for kinetic energy, and we're going to explain why there's a difference. So using the guess method, we write down the values that we've been given. I should have written out the value that we didn't know there as well, but that was EP. So EP equals mgh, which gives us 975,000 joules. So that was before the cable broke. We can see that after the cable broke and just before the container hit the ground, the kinetic energy was 970,000, and so the difference, 975,000 minus 970,000, gives us a difference of 5,000 joules. Those 5,000 joules need to be accounted for, and that's what the explain is. And so when an object's falling, there's a loss of gravitational potential energy through friction with the air, and that might be released as sound energy or thermal energy. So what I've written here is there's less energy just before the container hits the ground because some of the gravitational potential energy was converted to sound and some was converted to thermal energy through friction because of air resistance. The remainder was converted to kinetic energy, and with these sorts of questions I find it's always useful to refer back to the law of conservation of energy, and so that would tell us that the sum of the kinetic, thermal and sound energy would equal the gravitational potential energy. Okay, I hope that's been useful for you. If you've got any questions, feel free to post them below.